Welcome back. Let's learn about level curves and contour maps. Alright, so in the previous lesson, you were introduced to multivariable functions, and at the end of the lesson, I briefly talked about how to graph them, specifically functions of two independent variables, which represent surfaces in 3D space, and I mentioned that you wanted to try to recognize if your function represented a special type of surface, such as a plane, cylinder, or quadric surface, and when that was the case, graphing the multivariable function is generally not too complicated. It's something that we can reasonably do. We have processes for graphing each of those special types of surfaces. But a natural question that you might be wondering is, what do we do if a function doesn't represent one of those special types of surfaces? One suggestion I gave at the end of the previous lesson is that you could use a 3D graphing calculator, which certainly will work, but there is another way to help us visualize surfaces or the graphs of multivariable functions by hand, and that is to use something called level curves. As a concept, level curves may be familiar to you if you've ever seen a topographical map, such as one for a mountain. Now this right here is not your typical topographical map. I'm showing you a 3D representation or a sketch of a mountain, and then its corresponding topographical map. Generally, you're just given the bottom part here. But I want you to see how these two things are related to each other because it is directly related to this other way I'm going to show you for how we can visualize surfaces. Alright, so for this mountain here, at different heights, paths along the ground surface are traced, and then those paths are compiled together to form one map that helps you visualize the shape of the mountain as well as how steep or flat it is at different areas. Okay, it's a way of visualizing a mountain, which is in 3 dimensions, but in a 2-dimensional format. Each of these paths that you see down here correspond to a path that was drawn along the actual mountain. You can think of these different measurements as being measurements of feet, just for this example here. You can think of this path as being 10 feet from the ground, this second path as being 20 feet from the ground, then 30 feet, 40 feet, and so on. And you can see that those paths directly correspond to those lines down here. The closer the lines are together, the steeper the mountain is in those areas, because if you think about it, each line represents a height of 10 feet. The closer those two lines are together, then there is a smaller amount of horizontal distance between those two paths. So it would have to be a steeper area of the mountain compared to an area over here where the lines are spread out a little bit more. Meaning that to get from a height of 10 feet to 20 feet on the mountain, there's a lot of horizontal distance here, and so you're going to make up that height distance gradually when you're walking up the mountain this way, as opposed to over here where you're almost going straight up. Okay, that's the idea here. The closer those lines are together, the steeper the mountain is in those areas. And we can do something very similar to this to help us visualize the graphs of surfaces represented by multivariable functions. For example, consider half a sphere. What we can do is look at curves at different values of z along that surface that we would call level curves and graph them together on one coordinate plane that can help us visualize the shape of that surface, as well as how steep or how flat it is at different areas. Alright, a level curve, like the ones you see graphed here, is the resulting shape when a plane intersects a surface at different levels along the axis of the dependent variable. Alright, so in our case, that is going to be z. Z is typically our dependent variable for our multivariable functions f of x, y. You can think of each of these level curves as being the result of what you would see traced in a plane that would intersect with that surface at different values of z. So think of the plane z equals 1. That would cut through the surface and capture all of the different points that have a z coordinate of 1, and all of those points would form a circle that we could then graph in this coordinate plane. And then you could look at another plane, z equals 2, and that plane would cut through the surface and capture another trace of a circle with all the different points that have that z coordinate of 2, and then you'd plot that curve, and you'd keep doing that over and over for as many different planes or values of z that you like, and all those different curves, which we are calling level curves, would help us visualize that surface once graphed together in a plane. And we actually call this graph here a contour map. It helps us see the contour or the overall shape of our surface. Okay, graphing multiple level curves on one graph creates a contour map. And another way of thinking about these contour maps is that you're looking at your surface from the top down, but in such a way that you're only looking at the traces of that surface in different horizontal planes that cut through different values of z along the z-axis. All right, we're essentially squashing this surface into the xy plane and then looking at all the different level curves that correspond to different values of z for that surface. Okay, and to give you a better visual of what I mean by that, here's a 3D render of a non-special surface that could be represented by a multivariable function. You can see that I have some different level curves already drawn on the surface for different values of z, but then what you could do is actually remove the surface itself and just look at those different level curves, and then look at all of those curves from the top down. So you're just looking at the XY plane, and there it is. That right there is a contour map composed of all these different level curves from the surface. Okay, so that's the idea of level curves and contour maps. That's what we're going to be doing here, but of course, we're going to be doing the work by hand. We're going to be finding some different level curves and then graphing them ourselves in an XY plane to create a contour map. And so speaking of which, let's take a look at how to do that next. In order to sketch a contour map, or sometimes you'll hear it called a contour plot, but I'm going to call them contour maps in my videos. In order to sketch them, you want to start by finding different level curves. And to find level curves for a surface, you want to set the multivariable function equal to different constant values of c. All right, those different constant values c are essentially just different values of z, your dependent variable, where you want to get a trace of your surface. Okay, and then once you have that equation where you're setting it equal to a constant, you want to try to get your equation, which should only be in terms of x and y at that point. You want to try to get it into a familiar form, an equation that you know how to graph in an xy plane. And those constant values of c, or the values of z that you're going to use to get those level curves, the values that you use are completely up to you unless you're told to use a specific set of constant values. Okay, if you're not told to use any values, it's completely up to you which ones you use, as long as they make sense to use, of course, right? You don't want to use a negative constant if it's impossible for your function to output a negative value. All right, you'll see what I mean by that in just a second. But generally, the values of c that you choose are up to you. Just make sure that they make sense, and also take this into account. The best contour maps, or the maps that are going to best represent your surface, are made by level curves where the c values that were chosen are evenly spaced, okay? And what I mean by that is that, let's say you choose c equals 1 and then c equals 2, just go on to c equals 3 as well. Don't go 1 to 10 or 1 to 20. Try to keep your constant values evenly spaced. All right, and if you're not quite following me yet, don't worry. We're going to take a look at an example. Let me show you what this process looks like. For this example, our multivariable function f of xy is equal to the square root of 9 minus x squared minus y squared. All right, now you could rewrite this function using the dependent variable. You could say that z is equal to the square root of 9 minus x squared minus y squared. What we're going to do here is essentially that, but instead of z, we're going to set the function equal to a constant c. All right, so we'll say c is equal to the square root of 9 minus x squared minus y squared. And then from there, you could choose different constant values to plug into that c in this equation, and then try to graph it. But to make that process easier for us, because I currently don't know how to graph this function in its current state, what you want to do is get this equation, now that you've set it equal to c, get it into a form that you do know how to graph before you start plugging in values of c. Okay, so what I'm going to do here is manipulate this equation a little bit. If you square both sides of the equation, you'll have c squared is equal to 9 minus x squared minus y squared, right? Squaring both sides gets rid of this square root over here, and then you just have c squared on this side. And then what I'm going to do is add x squared and y squared over to this side of the equation and subtract c squared from this side. So I'm going to move it over to this side of the equation. And what you'll be left with is this: x squared plus y squared equals 9 minus c squared. Okay, once again, I subtracted c squared from both sides of the equation, and then I added x squared and y squared to both sides. And so this is what you should get. And this right here is the equation of a circle, right? You have x squared plus y squared is equal to some constant value, which would be the radius squared. Okay, remember, c is just a constant, so what's going to happen over here is you're going to plug in some value for c, square it, and subtract it from 9, and you'll just have some constant equal to x squared plus y squared. That is the equation of a circle. All right, so what this tells us is the different level curves that we're going to get, they are going to be circles that just have different values for the radius. All right, our level curves are circles. So let's take a look at some of these level curves. We want to pick some constant values to plug in for c, but you have to make sure to pick some that make sense. So remember at the beginning, c is equal to the square root of 9 minus x squared minus y squared. A square root is never going to output a negative value. In other words, there will be no negative outputs for this function. Those negative values would not be included in the range for this multivariable function, so don't pick any negative constant values to plug in for c in this equation. All right, so be careful about that, but what we can start with here is just c equals 0. The square root of a function can be equal to 0, so let's look at the level curve when c equals 0. We're going to have this equation, but where c is 0. 0 squared is 0, you're subtracting 0 from 9, so you're just going to have the equation x squared plus y squared equals 9. All right, so when c equals 0, this is the equation that we get. It's just a circle with a radius of 3, right? X squared plus y squared equals the radius squared, and 9 is 3 squared, so the radius is 3. That's one level curve. Let's take a look at another one. I'm just going to increase my c value by 1. So let's look at c equals 1. What would the equation for that level curve look like? If you plug 1 in for c here, you'll have 9 minus 1 squared. 1 squared is 1. 9 minus 1 is 8. So you'll have x squared plus y squared equals 8 for the equation when c equals 1. That will be our next level curve. X squared plus y squared equals 8. In that case, the radius would be the square root of 8. I didn't write this down before, but I'll write it down now. Last time the radius was 3. This time the radius is the square root of 8. And then let's take a look at another level curve. You're going to want to look at least 3 or 4, if not more, when you're sketching these contour maps. So don't just stop at 2 level curves. Try to find 3 at the very least, but in most cases you're going to want more than that. And so when I pick my next value of c here, I'm not going to skip by a bigger amount than I did last time. I want to try to choose values that are evenly spaced. So we went from 0 to 1. Let's go from 1 to 2. All right, c equals 2. When c equals 2, plugging 2 into our equation here, 2 squared is 4, 9 minus 4 is 5, so you'll have x squared plus y squared equals 5. All right, so this time around, our level curve is represented by x squared plus y squared equals 5. So in that case, we have a circle with a radius that is equal to the square root of 5. Once again, all of our level curves here are going to be circles, but just with different radii. But then let's find another one. Let's look at c equals 3, which is actually the biggest value of c that we could pick for this problem. Because if you think about this function here, you're taking the square root of 9 minus some value that results from x squared plus y squared, right? You could pull out a negative here and you'd have 9 minus x squared plus y squared. The smallest value x squared plus y squared could be is 0, because x squared plus y squared is always going to output a positive value. So the smallest it could be is 0, meaning the smallest number that would be subtracted from 9 is 0. And so the square root of 9, which is 3, is the biggest output for c. Okay? It's just like thinking about the range for your function like we did in the previous lesson. All right, but when c equals 3, you'll have 9 minus 3 squared, which is 9 minus 9, which is 0. So our equation is x squared plus y squared equals 0, which is a circle with a radius of 0, which means it's just a dot. It's just a point at the origin of the xy plane. And so now we have all the equations for the level curves that we're going to use to help us visualize this surface. What we want to do now is graph each of these level curves in this xy plane. And so let's start by graphing the level curve for c equals 0, which will just be a circle that has a radius of 3. So if this is y equals 3, x equals 3, y equals negative 3, and x equals negative 3, that level curve will look something like this. That would be the level curve when c equals 0. Moving on to our next level curve, for c equals 1, we have another circle, but this time the radius is the square root of 8, which as a decimal is approximately 2.83. And so that will be the radius of this circle. And so if this is y equals 2, x equals 2, y equals -2, and x equals -2, a radius of 2.83 will get close to 3 in each direction, but not quite get there. Alright, so that circle might look something like this. And so that circle would be our level curve for c equals 1. Now moving on to c equals 2, we have another circle, but this time with a radius of the square root of 5, and as a decimal, the square root of 5 is approximately 2.23, and so a radius of about 2.2 would take you a little bit above 2 in each direction. Alright, so that circle might look something like this. That circle would be the level curve for c equals 2. And then finally, we have one more level curve for c equals 3, and this is probably the easiest one to graph. It's not really a circle at all. The radius is 0, so it's just a point at the origin. Alright, so I'll plot a point at the origin, and that would be the level curve for c equals 3. And that's it. That is a completed sketch of a contour map for the surface represented by this multivariable function. This contour map gives us a top-down view of our surface where we're looking at different traces of that surface at different values of z, those constant values that we chose to plug in to this equation to get our different level curves. And so you can see now that from this perspective, the lines are closer together towards the outside of the surface, and they are more spaced apart as you get closer to the center of the xy plane. So this surface is steeper around the edges and a little bit more flatter towards the center, at least from this perspective. Alright, now you may have been able to guess, based on this contour map, along with the form of this function, that this represents half of a sphere, or a semisphere. And so just to compare the actual surface to our work here, here's a 3D render of that semisphere, with some different level curves graphed on top of it. I included a few more than what we graphed in our contour map, just to give you a better visual, but we didn't have to do that in our sketch. As long as you pick values of c evenly spaced apart, you're fine. But you can see that if you were to look at this semisphere from the top down and only look at the level curves, that you get a very similar contour map to the one that we drew here. Alright, so hopefully that helps you make the connection between the actual surface represented by our function and the contour map that we drew using level curves. Okay, so that's it for this initial demonstration of sketching a contour map. We're going to take a look at a couple more examples in just a second, but first, just a couple notes that I want to highlight here. We sort of already talked about this, but assuming that you are using equally spaced c values to find your different level curves, and then you graph those curves in a contour map, the more visual space between the level curves, the less quickly z is changing with respect to x and y. In other words, the surface is more flat or less steep in those areas. Okay, the output for the function z is not changing as rapidly as it may be at other parts of the surface. Okay, but then on the flip side, the less visual space between level curves, the more quickly z is changing with respect to x and y. In other words, the surface is more steep in those areas. Okay, so in those areas for the surface, the output values of z for the function are changing more rapidly. So I just wanted to make a note about this here. We're actually going to look further into how z is changing with respect to x and y later on in Calculus 3, so stay tuned for that, but that's not the focus of this video. For now, we just want to work on finding level curves and sketching contour maps. And so let's actually move on to another example of that. Hey there, real quick, before we get to the next part of this lesson, if you find my tutorial videos here at JK Math to be helpful, then I'd like to invite you to join my membership site, JK Math Plus, where you get access to many perks, including bonus content and my exclusive community. The bonus content includes dark mode versions of my videos, extra example problems, and more, while the community is a private space online where you can post questions, have discussions, and study together with me and other members. To learn how to join and see a full list of everything you get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. So if you are interested in becoming a member, feel free to check that out. It's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's get back to the lesson. Okay, so for this example, we want to describe the level curves of the function and sketch a contour map of the surface. All right, and we have our xy plane here already to help us sketch the contour map. So if you're following along, be sure to draw yourself an xy plane as well. But our function here is f of xy is equal to y squared minus x squared. Okay, so the first thing we want to do is figure out what the level curves will look like for the surface represented by this multivariable function. That's what the problem means by describe the level curves. We want to figure out what general shape are we going to get for our different values of c. In our first example, all of our level curves were circles, but that's probably not going to be the case here. And so let's take a look. What we want to do is set our function equal to a constant value c. All right, so we're going to have c is equal to y squared minus x squared. And so then what we want to do is try to get this equation in the form of some type of curve that we recognize. And the first thing I'm going to do is just flip the two sides of the equation. This just helps me recognize the equation a little bit better when I have the variables on the left side. So I'll write y squared minus x squared is equal to c. And then notice that if we were to divide both sides of the equation by this constant value c, our equation would be in the form of a hyperbola, right? Dividing both sides by c will give you y squared divided by c minus x squared divided by c is equal to 1, because c divided by itself would be 1. And this right here would be the equation of a hyperbola. It looks very similar to the equation of an ellipse, except one of the two terms for y squared or x squared is negative. In this case, the x squared term is negative. All right, so our level curves here for this function will be hyperbolas. That is what we have found here. That's how we can describe the level curves. All right, so once again, this is always your first step. Set your function equal to that constant value of c, and then try to manipulate the equation into a form such that you recognize the type of curve that the equation represents. Okay, in this case, hyperbolas. But now let's actually find some of these level curves. Let's start plugging some different constant values in for c. And so I always like to start with c equals 0. That might seem like a problem at first, because if you're looking at this form of the equation, you can't divide by 0. But if you go back one step to this equation, you can have the equation y squared minus x squared equals 0, right? That is an equation. You might not quite remember what that represents, but what that is a degenerate hyperbola, okay? Instead of your typical hyperbola, which has two different curves, a degenerate hyperbola, specifically this one, y squared minus x squared, is a graph where you have the line y equals x and y equals negative x, okay? That's what this equation represents, right? You could solve for y squared here. You'd have y squared equals x squared. Take the square root of both sides, and y equals plus or minus x. So that gives you the two lines y equals x and y equals negative x. Okay, so that's just a degenerate hyperbola. That's our level curve for c equals 0. But then let's move on to another value of c. I'm just going to move up by 1 to c equals 1, and then keep that same spacing for all of my constant values. So let's look at c equals 1. Now we can plug that value of c into this form of the equation, but really it's just going to be the same thing as up here, because y squared divided by 1 is y squared, and x squared divided by 1 is x squared. So we do just get y squared minus x squared equals 1. And that would just be a regular hyperbola. And so then let's look at c equals 2. If you plug 2 in for these two c's, you get y squared divided by 2 minus x squared divided by 2 equals 1. And then let's do one more. Let's look at c equals 3, and you'll get y squared divided by 3 minus x squared divided by 3 equals 1. All right, we just replaced each of these c's with 3. And so these three equations, or these three level curves, are all regular hyperbolas. They just have slightly different shapes because of those denominators changing for y squared and x squared. We'll talk about how to graph those in a moment, but before we do, we can actually look at negative values of c here as well. We couldn't in our first example, because our function was a square root function. There is no way to output negative values. But in this case, y squared minus x squared can be negative, right? This constant value of c that would result from this subtraction could be negative because the value of x squared could be bigger than y squared. So it does make sense to look at some values of c here that are negative. And when you can do that, you should at least look at 1 or 2. It won't always be helpful, but many times it will be. So let's look at a couple here. Remember to keep the same spacing. So let's go from c equals 0 to c equals negative 1. So for c equals negative 1, something interesting is going to happen here. we're going to divide both of these two terms by -1. So the signs are going to change. Instead of x squared being the negative term, y squared will be the negative term. So I'm going to rewrite the equation like this. You'd have x squared minus y squared equals 1. All right, the y squared term is now negative and the x squared term is now positive, and I just flip their placement in the equation so that it looks a little bit nicer. We now have x squared minus y squared rather than y squared minus x squared when c was positive 1. All right, and if we were to look at c equals -2 and -3, a very similar pattern is going to occur. We're going to have the same equations that we did for c equals 2 and c equals 3, except the signs of these two terms are going to flip. For c equals -2, you'll have x squared divided by 2 minus y squared divided by 2 equals 1. And then for c equals -3, you'll have x squared divided by 3 minus y squared divided by 3 equals 1. All right, that's what we would get when plugging c equals -2 and -3 into this equation. And so now that's enough. I think we have plenty of level curves here to graph in this plane to get a sketch of the contour map of the surface represented by this function. And so let's start with c equals 0. As I already mentioned earlier, that is a degenerate hyperbola, which in this case will just be represented by two lines, y equals x and y equals -x. So let's graph those here. This will be y equals x and y equals -x. And so that right there is our level curve for c equals 0. But then let's move on to c equals 1. How do we graph y squared minus x squared equals 1? That is a hyperbola, specifically one that is directed along the y-axis because the y term is positive. All right, if you don't remember how to graph your conic sections, you're going to get a quick little review here. Whichever variable term is positive, the corresponding axis is the one the hyperbola is directed along, and then the square root of whatever the positive term is being divided by, that will give you the values of the intercepts along that particular axis. All right, so in this case, y squared, the positive term is being divided by 1 technically, and the square root of 1 is plus or minus 1, so we know that the two curves for this hyperbola will be directed along the y-axis and cut through y equals 1 and y equals -1. All right, so if this is y equals 1 and this is y equals -1, one of the curves for that hyperbola will look like this, and the other one will look like this. All right, that is c equals 1. Now let's move on to c equals 2. The y term is still positive, so we're still going to be directed along the y-axis, but this time the square root of 2 will give us our y-intercepts, and as a decimal, the square root of 2 is approximately 1.4. So assuming that this is y equals 2 and y equals -2, about halfway to 2 in each direction will be the intercept for the curves of this hyperbola. So one of them would look something like this, and the other one would look something like this. All right, that is the level curve for c equals 2. Now let's look at c equals 3. The y term is still positive, so we're still directed along the y-axis, but now the square root of 3 will give us the intercepts. And so as a decimal, the square root of 3 is approximately 1.7. So we're going to be even closer to 2 in each direction. So one of the curves for the hyperbola will look like this, and the other one will look something like this. That will be c equals 3, or the level curve for that value of c. And so that takes care of all of our level curves for positive values of c, but what about our negative ones? -1, -2, and -3. Well, in each of these equations, the x term is positive, but everything else basically remains the same. So we're going to have the same hyperbola as we just drew here, but now they're going to be directed along the x-axis. All right, so for c equals -1, we'll have two curves with x-intercepts of 1 and -1. Then for c equals -2, the intercepts will be plus or minus the square root of 2, so 1.4 in each direction. And then for c equals -3, the intercepts will be plus or minus the square root of 3. So let's graph those hyperbolas here. This is x equals 1 and x equals 2, and then x equals -1 and -2. For c equals -1, we'll have a curve like this, and a curve like this. That's for c equals -1. And then for c equals -2, we'll have an intercept of about 1.4. So one of the curves will look like this, and then in the negative direction, the other one will look like this. That is c equals -2. And then finally, for c equals -3, the intercept is about 1.7, which is the square root of 3. So that's one of the curves. and then here's the other one in the negative direction. That will be c equals -3. All right, and so now we're done. That is the contour map that features all of the level curves that we found here. This gives us a way to sort of visualize the shape of the surface represented by this function. All right, and if you were to look at the surface represented by this function, here's a 3D render. Once again, I've included level curves on the surface. I've included more than we drew in our contour map just to give you an even better visual. But here you can now actually see the shape of the surface. And then when you look at it from the top down, so that you're only looking at the level curves from the perspective where you're looking at the XY plane. So think of it as squashing the surface into the XY plane. Now you can see all those level curves, which should look very similar to the contour map that we sketched here. Okay, and so that's it for this example. Let's take a look at one more for this lesson. Alright, so once again, we want to describe the level curves of the function and sketch a contour map of the surface. And this time around, unlike our previous two examples, we actually have a surface here that we're not going to recognize as one of our special surfaces. Right, our last two examples featured half of a sphere and a hyperbolic paraboloid. Those are special surfaces that we learned about earlier in Calculus 3, and so those are already surfaces we know how to sketch. So a contour map is maybe not as helpful as it will be for other functions such as this one, which we do not recognize what it looks like. Alright, our function here is f of xy equals the natural log of x plus y. I have no idea what that looks like without putting it into a 3D graphing calculator. But we can get a good idea of the shape of the surface by making use of level curves and a contour map. So let's work on that here. The first thing we want to do is set this function equal to a constant value of c. So we'll have c is equal to the natural log of x plus y. And then what we want to do is try to get this equation in a form of some type of curve that we know how to graph. All right, and right now, I don't know how to graph this, so let's try to manipulate it a little bit. What we can do is exponentiate both sides of the equation using e. So we'll have e to the power of c is equal to e to the power of the natural log of x plus y. And so then e and the natural log will cancel each other out, just leaving you with e to the power of c is equal to what is inside that natural log function, which is just x plus y. That is all that gets left over after e and the natural log cancel each other out. And so now, if we solve for y here, you'd want to subtract x from both sides of the equation. That will give you this. Y is equal to negative x plus e to the power of c. That right there is an equation of a line, right? Y equals negative x is to the first power. This is a linear equation, and then you're just adding some constant of e to the power of c. That will be the y-intercept for that line. So all of the lines are just lines with a slope of -1, right, the coefficient of x, and then a y-intercept of e to the power of some constant. Okay, so that's how we would describe these level curves. But now let's actually find some level curves and then sketch them in our xy plane. I always like to start with c equals 0 if I can, and we can in this case. If you plug 0 in for c, you will get the line y equals negative x plus e to the power of 0, right? You plug 0 in for c, and anything to the power of 0 is 1. So we get negative x plus 1. All right, so that's one of our lines. That's pretty nice. Let's look at another value of c and find another level curve. I'm just going to use a spacing of 1 once again. So let's look at c equals positive 1. That will give us y equals negative x plus e to the first power, which would just be e. So we have negative x plus e. And then let's look at c equals 2. Remember to keep the same spacing between your c values. That way you get a nice contour map. In this case, we'll get y equals negative x plus e squared. And then let's do one more. C equals 3 will give us y equals negative x plus e cubed. Okay, now you could look at negative values of c as well, but they're not going to be all that helpful here, because in each case, the only thing that's changing is this y-intercept. And so we go from 1 to e, and e is about 2.7, right? E is approximately 2.7, and then e squared and e cubed are just going to be bigger values than that. But if you use a negative value of c, such as c equals -1, you'll have e to the power of -1, and e to the power of -1 is 1 divided by e. which is a very small value. It's a positive value, but it's very small. And as you would pick more and more negative values, such as a -2 and -3, that value is only going to get smaller and smaller towards 0. So you're just going to have lines with y-intercepts getting really close to 0, which is not really easy for us to graph. So I'm going to stick with our positive values of c here, and that will be good enough, okay? But now let's actually graph these level curves. Before I do that, let's get some approximate values for e squared and e cubed. That will just help us know what our y-intercepts are going to be for these lines and how we should draw out the scale for our y-axis. And so e squared is approximately 7.4, and e cubed is approximately 20.1. So that intercept is getting bigger pretty quickly. All right, but now let's graph them. Keeping these different y-intercepts in mind, I'm going to let this be y equals 20, this will be y equals 15, y equals 10, and y equals 5. And I'll do the same thing in the x direction. This is 5, 10, 15, and 20. So for this one here, y equals -x plus 1, the y-intercept would be at 1, which is somewhere right here, and then you have a slope of -1. So if this is y equals 1 right there, then the line might look something like this. All right, that would be the line, or the level curve, for c equals 0. Then let's move on to c equals 1. The y-intercept is about 2.7, so I'll say that that's about right here, which means that our line will look something like this. That would be the line, or the level curve, for c equals 1. Then let's move on to c equals 2. The y-intercept is now a lot bigger, it's 7.4, so that's somewhere about right here, between 5 and 10. So that line would look something like this. That will be the line, or the level curve, for c equals 2. And then finally for c equals 3, the y-intercept for this line is 20.1, which is basically 20. So I'm just going to draw a line right through y equals 20. Okay, now all those lines should be parallel. I didn't really do a great job at that here, but you get the idea. All of these lines have the same slope, so they should all be parallel. It's just that they intercept the y-axis at different points. Okay, so that line right there is our level curve for c equals 3. And so that would be our contour map for the surface represented by this function. It doesn't seem to initially give you that much information about the shape of this surface, but it does help in that there's really not a ton of curvature for the surface when you're looking at it from the top down. And that is exactly what you'll find if you do look at this surface. And so here's a 3D render of it with some more level curves than what we drew in our contour map. Once again, I included more, so you have a better visual to help you get a better understanding of what we're doing here. And you can see that this really isn't a surface with a whole lot of curvature. It is pretty flat most of the way, which is reflected in our contour map. And so if you do look at the surface from the top down, just looking at the level curves, you will see a very similar contour map to what we sketched. All right, all of the level curves are lines. And so with that, that is it for this example, which is the last example for this video of sketching a contour map. But before we close out this lesson, there's one more thing I want to talk about, and that is the idea of level surfaces. In this video, we have really only looked at multivariable functions of 2 independent variables, but for functions of 3 independent variables, which represent 4-dimensional graphs, we can find level surfaces, which would be graphed in 3 dimensions, right? Just like for our functions of 2 independent variables, their graphs are in 3 dimensions, but their contour maps are in 2 dimensions, where we plot different level curves, so everything is 1 dimension less than the actual graph. The same thing happens here. For 4D graphs, 1 dimension less would be 3 dimensions, which would capture the level surfaces of whatever that 4D graph looks like. Okay, so because these functions do represent 4-dimensional shapes, we don't really have a nice way to visualize that, but we can at least determine the shapes of the level surfaces for those functions. And so as a quick example here, we're just going to identify the type of level surfaces that this function would have. There's no real purpose to then graphing them in the 3D coordinate system. We just want to figure out the type of level surface, and the process is nearly identical. We're just going to set our function equal to a constant value c, and then try to get the equation in a form that we recognize how to graph in 3 dimensions. So in this case, we would have c is equal to 5x plus 2y minus 4z plus 3, right? Our function is a function of 3 independent variables, f of x, y, z, so it is in terms of x, y, and z. But now, if we make one simplification here, or if we just change one thing about this equation by subtracting 3 from both sides of the equation, you get an equation like this. 5x plus 2y minus 4z equals that constant value of c minus 3. And I did flip the sides of the equation just so it's a little bit easier to recognize what we're looking at here. This is the equation of a plane, right? X, y, and z are all to the first power. There's no squares anywhere. It's just x, y, and z, where each of them have a different coefficient, and all of them together are equal to some constant value. That's all this is. C minus 3 is just a constant. Once you plug in a value of c, you'll subtract 3 from it and get a single value. And so this is just the equation of a plane. So the level surfaces for this function would be planes, in particular planes that have a normal vector with components of 5, 2, and -4, right? So the level surfaces here are planes with a normal vector that has components of 5, 2, -4. The x, y, and z components are just the coefficients of the x, y, and z terms, respectively, in the plane equation. Okay, so that would be the final answer to this example, where we want to describe the level surfaces of the function that represents a 4D graph. And so that's it. So you use the same process that we used for our level curves for functions of 2 independent variables. It's just that you need to identify a type of surface rather than a type of curve. Okay, and so that's it for this lesson. If you want to get some more practice finding level curves and sketching contour maps, feel free to check out the examples video for this topic that I'll have linked here on the screen. If you have any questions, please let me know in the comments, but if you don't have any questions, this is all I had for now, so I will see you next time.